Oh, my goodness, I cannot believe it is lesson 10, the end of summer. This is kind of bittersweet. I know y'all are, excited to be done with the math program, but at the same time, you have to go back to school. And I just want to tell you, I've had a great time with precal this summer. Precal is probably my favorite subject, and I am not shy about saying that, and it's just been awesome working with you guys and girls. So, what we're going to talk about to close things out is a function that you did last year. It's a parent function that you did last year, and it's a rational function, and we're going to close out all the parents with this. I don't know at what point in the year you're going to do it. I'm thinking in the spring, probably, I don't know, March, April, something like that is my guess. But who knows? It depends on your teacher. So we're going to first start about talking about rational expressions and simplifying those expressions. So an example of this is going to look like the following. We're going to have, remember, rational just means something that can be written as a fraction. So I'm going to have some kind of fraction divided by some kind of fraction, and I'm going to make it look maybe a little something like this. Okay, maybe something like that. So if a problem like this is given to you, first of all, with division, you have to remember what it means to divide a fraction. And hopefully you remember that when dividing fractions, you need to flip the second and multiply. So I'm going to start by rewriting this where that's a multiplication, and then I just do the reciprocal over here. That would be a really good first step, okay? So, and actually, I'm going to do two steps in one because I don't have a whole lot of room down here. In the same step, I'm going to go ahead and factor each piece of the fraction. The biggest mistake you could make is actually multiplying things out or actually dividing things out. On these, you always want to start with a factor approach just in case stuff cancels, okay? So let me just factor out a 2 here. And in the denominator here, you hopefully recognize that that's a difference of squares. And it can become x plus 3 times x minus 3. Now I'm going to do what I told you. I'm going to do times, and I'm going to flip the second fraction. So x minus 3 is now on top. And on the bottom, I'm going to try to factor that out as well. It looks like that will be x plus 2 and x plus 3, okay? So what you're going to want to do from this point is, like I said, factoring is a powerful thing because now that this is multiplication, you can cancel anything top to bottom that will actually cancel. So in other words, this x minus 3, I'm going to cross out completely because there's another x minus 3 over here. And this x plus 2, I'm going to cancel out with this x plus 2, okay? Now, don't cancel out these because they're both in the denominator. So you have to have one on top, one on bottom. But now it's a simple problem, and you just take what's left in the numerator, which is a 2, over whatever's left in the denominator. And whatever's left here, I could write that twice, or I'm going to just put a squared on it since it's the x plus 3 times x plus 3. I could write it like that. And you're done from here. You don't need to FOIL it out or anything like that. This is it. You're finished, okay? Now, other simplifying would be, what if it's an add or subtract, okay? If it's add or subtract, I also still start with a factoring approach because that helps me find the common denominator. We are going to have to find the CD, the common denominator. So, let's take a problem. In fact, let's take the problem we just did. I'm just going to change it up just a little because I am. X squared minus 9. I'm going to put a plus sign now. And I just want to make this numerator a little friendlier because it would be a very long problem otherwise. Okay, so here's a new problem, a new example where we're adding two fractions. So we need a common denominator. So I factor first to help me find the common denominator. And guess what? I don't actually usually factor the whole thing. I usually just factor the denominator. I should sneak that in. I factor the denominator first to help me out. So this right here, x squared minus 9, is really x plus 3, x minus 3. And so that was a really good decision to factor it, because now the common denominator is x minus 3, because both of these have an x minus 3, but also x plus 3. Okay, so my common denominator is x plus 3 times x minus 3. And the numerator just stays the same, because I did not have to add anything to this denominator, or I mean multiply anything by this. So since it already has both components of the common denominator, I just get to keep the numerator. Now I recopy the plus sign. Now over here, the common denominator is still x plus 3 times x minus 3, but let's take a look at this. X minus 3 and x minus 3, it already had that. So that's like, yay, it already had that. It was missing this one. So I just need to think, well, I actually just changed this by multiplying it by x plus 3. So whatever you do to the bottom, you're going to have to do to the top. Okay? So this whole thing, this whole x plus 1 has to get multiplied by the x plus 3. So this is just getting a common denominator on steroids, okay? Like it's the same thing you do with numbers, but now we've got binomials that we're doing this with. So the bottom just stays the same, and the top's going to become all of this, x plus 1 times x plus 3, and now you kind of do want to FOIL that out, or multiply that out. And the reason for that is because if you multiply that out, everybody, now in the numerator, remember when you add fractions, you get to now add both the numerators together. And if there are any like terms, we can put them together. So in the numerator, I see an x squared, yay, and what else do I see? Okay, a 2x plus a 4x, so those go together. And then I've got a plus 4 here and a plus 3 there. So I'm just combining like terms in my numerator. I'm crossing them out as I go. All over x plus 3 times x minus 3. And you are finished. There's no reason to ever multiply out the denominator. You don't have to do that. So once you factor it in the beginning, leave it that way throughout the problem. The numerator is the one that you get to leave kind of raw and ugly and do your distributing and your FOILing and combining like terms. Okay? So hopefully that made a little bit of sense. That's hard to do with just one example and a little bitty box, so it's kind of crammed. But hopefully, rewind if something was weird there that I said. Okay. So now the fun stuff. So once you learn how to deal with just fractions, then it starts to get really interesting, and you start graphing them. Okay, now these were the funky graphs. I'm going to remind you of what the parent looked like. Okay, the parent for these was that that thing that had asymptotes like everywhere, like asymptote here, and then it had like that swoosh. I call it the swoosh graph. I know that's not very technical, but I actually do call it the swoosh graph. Okay, so that is what it looks like, and it can be moved all around, and all kinds of things can happen. And so the most important parts of the graph are listed right here. And so I'm going to remind you of how to take an equation and find all 4 of these parts, and hopefully that'll help you with graphing, okay? So I'm going to use the same equation for every single thing that we do so that it's consistent, and then at the end we can graph that same equation. So I don't know if you want to put this in a big box or something or on the side. I'm going to kind of write sideways. We're going to be studying this equation for all 4 of these boxes, okay? Y is equal to, all right, what do I want this to be? Let's do x squared minus 16, and then x squared, let's do, let's do that. Okay, so this is the equation that we are going to be doing for all 4 of these, and the first thing, I put them kind of in the order of how my brain actually thinks, okay? So when I see these equations, the first thing that I do is see if they factor. Because if this equation factors, like if the numerator and the denominator factor, if something factors and cancels, the term that cancels actually creates a whole, okay? So if it cancels, you are going to have a whole. And I'll remind you of how to do that. That's the word cancel, by the way. It looks like canal. This is not a canal. All right, cancel. There we go. And then whatever doesn't cancel, okay, so the factor in denominator that doesn't cancel is your vertical asymptote. And hopefully that makes sense. The reason for that is because that is the place where the denominator would be equal to 0. And if you plugged in a number and it made the denominator 0, then that's undefined and it's all wacky. So it creates an asymptote on the graph, okay? So let's take this equation and let's math it out, okay? The numerator looks like it does factor into x plus 4 and x plus 2. The denominator definitely factors because it's a difference of squares again. Awesome. And now when I'm looking at this, something does in fact factor. I mean cancel, right? This cancels with this. So since this is the term that canceled, then I know there's going to be a whole at x equals -4. Now, why -4 and not +4? Because that says x plus 4, right? Well, remember, just like when you're solving these things out, you want to think in your mind, set this to 0, what would it be? And if you set this to 0, -4 is what your x would be. And so just be really careful with your signs there. Always set it equal to 0 whenever you're finding a number right here. Now, there's a whole at x equals -4. And unfortunately, that's not good enough to leave your answer like that. Your teacher's going to want you to write that as a point. Okay? It's because the whole happens at a coordinate. And the way that you're going to find that is you're going to take that x of -4 and you're going to plug it into whatever is remaining, okay, because that's the x and there's x's left, right? So let's mental math it. -4 plus 2 is -2 over -2 over, what's -4 minus 4? That would be a -8. So -2 over -8, that is your y value. Now that obviously reduces to 1/4. So I'm going to clean that up right there, okay? And that would be where your whole is located. So I've seen a few teachers that are okay with this answer, but I was not. I was very picky, and I'm like, the whole is a whole, and it happens at a point. So tell me the point. Don't just tell me the x value, okay? Now, what is left in the denominator? Well, the factor that's left in the denominator is x minus 4. So what I know about that is since x minus 4 is left in the denominator, there is a vertical asymptote at x equals +4. Same thing, you're going to set that equal to 0, and that's where the vertical asymptote's going to happen. Okay. Now, the reason I do domain next is because domain is the place where x can and cannot exist. And I just found that place. So as soon as I find my vertical asymptote, I'm like, oh wait, if there's a vertical asymptote at 4, then I know that the domain is all real numbers except x can't equal 4. And this is one way of writing whatchamacallit, domain. I'm going to write a few different ways. I've seen this as shorthand. This is technically set notation. I have seen a set bracket, and x is an element of all real numbers. This line means such that x cannot equal 4. So I've seen that before. And I've seen interval notation. So remember, with interval notation, you say, okay, well, I can start over here at -infinity and go to 4. but I have to skip 4, and then I pick up again, and I go all the way out to infinity, okay? So that is one way of doing it. Now, I realize as I'm talking, I did not talk about the whole. Silly me. Okay, I did not talk about the whole, and that is a mistake. So I need to erase some stuff. I'm actually going to have to erase this, because both of these places is where things are going wonky. So I should have added -4 here. I should have added a plus or minus 4 here. And that just means that on my interval notation, this is going to be crazy because I have to skip over both. So I'm sorry if y'all were writing in pen. Go erase, and let's go back and find a way to fit that -4 back in. Oh, wow. So I would not use interval notation on this problem just because, good grief, that's a lot of stuff to omit. You have to skip -4, then you have to go all the way to 4 and skip it, and then keep going. So I probably would have done one of the above. The above is what you'll use in college. This is called set notation, and like I say, I use this all the time in college. So I at least want you to see it, even if you don't plan on using it. Okay? All right, cool. So now we've got wholes, vertical asymptotes, and domain. In behavior asymptotes, now you might be thinking, what? We never did an in behavior asymptote. Yes, you did. Remember last year when y'all had to study horizontal versus slant asymptotes? That's the same thing. We're going to call it an end behavior asymptote in precal because it dictates what's happening on the ends of your graph. Okay, so it's the asymptote that tells you on the right and on the left, my graph better be approaching this horizontal line or this slanted line. Okay, now how do we find it? Okay, there were 3 rules. The first thing is you want to look at your problem and you want to analyze the highest powers. I'll put the highest powered terms of the numerator and the denominator. Okay, and your analysis is, once you look at that problem, one of 3 things is going to happen. You're going to look at the highest power term of the top and the bottom, and let's just do it with this. Look at what we have back here. After we cancel these out, this is our new problem. So what's the highest powered x term from up here? Well, there's an x, right, in this problem. And what's the highest powered x term of the denominator? Once again, it's just an x. So this is case number 1. Case number 1 is that the powers match, right? And, you know, if this is your problem and the powers match, all you have to do is reduce the coefficients. Okay, matching powers. The coefficients are the horizontal asymptote. So for instance, this problem above, okay, since it's x over x, I would reduce x over x and I'd have 1 over 1, which is 1. So I would say there is a horizontal asymptote at y equals 1. So that's the answer for the problem we just did. But sometimes if you pull the highest powered term here and the highest powered term here, sometimes you have a larger power in the denominator. Okay, so if you have a larger power in the denominator, these are my favorite, the asymptote, it's always a horizontal asymptote at y equals 0. So there's no math that has to be done. If you notice that, just put 0, and that's where the horizontal asymptote's going to be. If there's a larger power on top, so in the numerator, then there's going to be a slant asymptote. And the stinky thing about these is that in order to find out exactly what the slant asymptote looks like, you actually have to do long division. Eek. Okay, so that's no fun, and I may, if it shows up in the homework, you might just want to skip it and then watch my video, and I'll go slow on a problem like that so you can see what I'm talking about, okay? This doesn't happen a whole lot because most teachers aren't that cruel. I usually only would throw one of those in on a homework assignment, and the rest would be one of the other two, just to save time, okay? Now, what about finding x and y intercepts? Okay, this is not bad at all. Finding x and y intercepts, guys, are the same on everything you ever do. If you want the x-intercept, you set the y to 0. And then if you want the y-intercept, you set the x to 0. That's it. It's just you're setting the opposite one to 0. It works on any parent function. Let me say that again. This works on any parent function all year. So when you get stuck and you want to intercept, just do this, okay? So let me do that with the problem I gave you. So if I need an x-intercept, the problem I gave was y equals x plus 2 over x minus 4. So I'm going to put 0 equals x plus 2 over x minus 4. Now, notice I didn't worry about the factor that canceled out. I'm not worried about it here. I didn't worry about it here. When you're finding pieces of the graph, you get to use the reduced version. Okay, so how do I solve this? Well, let's think about it. When does a fraction equal 0? Well, a fraction equals 0 when the numerator equals 0. Or you can just think, well, let me simplify this by multiplying both sides by x minus 4. So I'm going to multiply both sides by x minus 4. Well, that side is still a 0, and I'm left with x plus 2 over here, right? So those cross out, I'm left with x. Now how do I solve for that? I move the 2 to the other side. So at x equals negative 2, I have an x-intercept, okay? So once again, let's write this as a point. So negative 2, 0 would be the point where it crosses. And so for a y-intercept, same kind of deal. Let me change colors of my pen. Okay, same kind of deal. Now it's 0 equals, no it's not, it's y. Okay, now I'm putting 0 in for x. So 0 plus 2 over 0 minus 4. And I reduce that and I get negative 1/2. So that is my y-intercept. And I will write that as a point. Usually y-intercept is the easiest for people because it's like, oh my gosh, I just have to plug in a 0 and solve. Yes, that's all you have to do, and it should be really quick, okay? So now that we have all the parts of our graph, we could easily sketch a graph down here, and that's what I'm going to do to end this video. And you are going to have a graphing calculator, a lot of you at home. So like if, sorry, let me do this. So if you want to check all your answers on a graphing calculator after you guess the graph, feel free. 1, 2, 3, 4, 5. Okay, let me put my intercepts on first. So my intercepts are at 0, negative 1/2, which is here. And what was the other one? Negative 2, 0. So I know I cross here and here. There's a horizontal asymptote at y equals 1. So I'm going to sketch that in. And where was my vertical asymptote? My vertical asymptote was at 4. 1, 2, 3, 4. But something else happened. Where was that hole? I need to go back up and look. The hole was at negative 4, 1/4. 1, 2, 3, 4, negative 4, and then 1/4. So it's like right there. And I know I drew it big. It's just because I wanted to see like what was happening. All right, cool. So these things look like the parent function. And remember, I drew that over on the side up here earlier. So once you find out where the asymptotes are and you have a few points to go by, you just play connect the dots. So I'm just going to connect all 3 of these, and that means this is probably going to keep going down. Now, something has to happen over here. Sometimes it's a piece down here, sometimes it's a piece up here. Now, I'm going to go ahead and guess that it looks like this. And then after I guess, I always take an x value that's over here, so any x you want. So 1, 2, 3, 4, 5. Let me take the x value of 5, okay? And I plug it into my equation. And the purpose for this is sort of just to check. It's like a guess and check. Like, okay, I'm guessing this. Let's see if this makes sense. So let's take the x value of 5 and plug it in. So if I plug in a 5, I get 7 over 1. Which is 7. So the point 5, 7 should be on my graph. Now look, lo and behold, I'm pretty good. 1, 2, 3, 4, 5, 6, 7. So it may need to be a little steeper, but you get the point. You just make sure that it makes sense with what you decided. But that's how these work, and I think they're fun. There's a lot of parts to find, but my favorite part is guessing what the picture's going to look like and then seeing how awesome I am if I'm right. Alright, so good luck on the homework. I know that's a long video, a lot of information. Not as long as some other weeks though, I guess. But good luck trying the homework, and we'll see you on the next video.